Hi everyone, welcome back to BioStat 100. For those of you in my lab section G5, welcome back. And for those of you not in G5, I hope you still find this helpful and glad to have you. So, as I'm sure you all know, you have a final for this class coming up, and I thought it would be helpful to go through some of the practice problems that Dr. Lee posted on BruinLearn. There were exactly three, so I figured we could go through roughly one a day, and I want to do this in pretty extreme detail. So you can skip around and feel free to kind of jump to sections that you find you need more help with. But I want to do this in a very self-contained manner. So where we go over basically everything from conceptual underpinnings all the way through the final calculation so that you can build up the confidence, skills, and background knowledge required to perform the best you can on the final. All right. So I guess before I get into it, as always, you can email me if you need to or have any questions at all. You should have my email on BruinLearn, and I'll also probably put it in the description of this video. And the last thing, which I think is very important, is for those of you in my section, and also for anyone in any section, please, please, please fill out your teaching evaluation form. This is super helpful for us because it not only tells us what we can do better on and what worked and what didn't, but it's also used by administration to choose teaching teams for future iterations of the course. This was actually my first time teaching the course, so it would be really great if I could get everyone in my section to just fill out the evaluation as honestly as possible. If there were things you liked, things you didn't like, I'd love to hear all of it. And I hope that it is comforting to you to know that we physically cannot see any contents of any evaluations until after your grades are finalized and put in. They're also fully anonymous forever, so we'll never know who wrote what. So please don't feel incentivized to write anything, either good or bad or what have you. Please be honest and just talk about your experiences in the class. And these are a really important way for us to get feedback, know if we're doing our jobs right as TAs, and also just giving us the feedback we need to be the best versions of ourselves. And it also tells administration who is effectively serving in their capacity as an instructor or maybe things to work on. So yeah, sorry, that was a bit of a ramble, but I will put in the description times you can skip to. But thank you so much. Please fill it out for me or any of the other instructors that you have, and let's get into it. All right, problem one. In a packing plant, a new machine is supposed to pack cartons faster on average than the current machine. The time in seconds for each machine to pack 10 cartons was recorded. Do the data provide sufficient evidence to conclude that the new machine packs faster? Test at alpha equals 0.05. All right. So the first thing I like to do when I see a problem like this is start highlighting. So you won't be able to do this on an exam probably, but let's just kind of get our bearings. The first things I'm seeing are new machine and current machine. This is signaling to me that we have two populations here. Oh, let's try a smaller font. Two pops. Okay. The second thing I'm seeing is the word faster. I'm seeing that word twice. And we'll get into why I think that's important. Another thing I'm seeing is time in seconds. And then if you look down, kind of spoiler alert, but you can see that these are decimal valued. So here what I'm seeing is continuous observations. So two populations, two samples is kind of implicit in that. And then I'm seeing that we're hypothesis testing here. And we have faster. So one machine, namely the new machine, is supposed to be faster than the current machine. So this is signaling to me that our hypothesis is going to be one-tailed. We're not interested in just a difference. We're interested in the difference having a direction. All right. So I think that's enough information to get us started. So the first thing that I'm going to do is I'm going to think through all of the possible ways that we could be doing this problem. So we have two samples and continuous observations. In this class, we've learned two ways to tackle comparisons like that. Another thing I should mention is we saw the word on average, so we know we're comparing means here. And the two ways we can do that are through z-based tests and t-based tests. This just says, does my test statistic follow a standard normal distribution with a z-test, or does it follow a t-distribution with a certain amount of degrees of freedom relative to our sample sizes, or a t-test? And in this case, I'm going to just scroll down a little bit, and it seems like they give us some information. So I'm going to highlight these in two different colors. You can ignore that like vertical line right here. That doesn't really matter. These are all independent observations of how long it takes each machine to pack 10 cartons. And I'm also going to do this color. Great. And because we hate algebra, we can see that we're given a little bit more info. We see that for the new machine, the mean time is 42.14 seconds. And for the old machine, it's 43.23 seconds. And we see that we have a sample standard deviation for the new machine as well as the old machine. And that should be our clue. If you see an S and not a sigma, generally that's indicating to you that we are using a t-test and not a z-test because we are estimating the population variance. So we have a t-test. Great. Next, we have two different modalities we could be considering. We have paired, so a paired sample t-test, or an independent. I'm just going to shorten that. All right. But when we look at this, let's think about it conceptually. We have two different machines recording their own observations. The new machine's observations, or times that it takes it to pack 10 cartons, don't really have any bearing on the old machines. Not in the same way as though like you're taking two separate blood pressure measurements on the same person spaced out a little bit, where the first measurement and the second measurement might have some correlation structure, or if you're doing a first like baseline test and then expanding upon it. These two are completely different machines and they're expected to perform differently. So I would say that this is an independent setting. Another thing to note is that, for example, if it were paired, we'd be pairing observations. So the fourth time that we record for the machine packing 10 cartons for the new machine doesn't necessarily pair with the fourth time that we do for the old machine. That doesn't actually have any significance. So we're not having any basis to pair observations. So we know we're in an independent setting. Okay. And now we still have a couple more decisions to make. So the next decision we're going to make is between a student's t-test or a Welch's. And so for this is pretty simple. It's just, are we assuming equal variances between our groups or not? If we weren't, we'd use a Welch's test, which basically just means our life gets a little more complicated and we have to use more precise degrees of freedom, often decimal valued. And if we're using a student's, then we might use a pooled variance and have a more simple degrees of freedom calculation. So a rule of thumb here is we can operate based on the ratio between our sample standard deviations. So we have S1 over S2, and we basically want to see if this ratio falls within the interval from 0.5 to 2. Now, what does this mean conceptually? It would basically mean that S1 or S2 should not be more than twice the size of the other or half the size of the other. We basically don't want them to be too far apart on a multiplicative scale. When we actually calculate this, we have 0.683 over 0.750, which is going to be exactly 0.91, which is not only within this interval, but it's actually very close to 1, which would be the case if we had both of the sample standard deviations the exact same. So that's great. Crudely and naively, we can assume that our population variances are going to be roughly equal, and we're going to use a student's t-test here and not a Welch's. And I will say generally, please don't quote me on this. I don't know what could happen on an exam, but I will say I think it's more common to encounter a student's t-test on an exam because Welch's t-tests are often performed computationally. All right, don't quote me on that, please. Um, and then there's one more decision which we've already made, which is between one-tailed and two-tailed. And like we said, we have that we already hypothesize a direction where the newer machine is going faster than the older machine. So I'm going to say two-tailed. Putting this all together, how would you write this out? You would say that we have a two sample independent students t-test, two-tailed. I think that's everything. Let's see. Looks like it. So that's a bit of a mouthful. Now we can kind of start getting into a little bit more of the math. Actually, we can't. We have to check our assumptions. So now that we've kind of defined the problem space, we want to know, is it even valid to perform a test like this? So I'm going to just zoom in and write assumptions. So there are a few assumptions that I want to cover. Some of them are implicit, like simple random sampling. We can kind of assume that based on the sampling procedure of checking how long it takes to fold 10 cartons over and over again independently. So I'll just write SRS check. Independence for this independent t-test. If we didn't have that, we just do a paired t-test. But I'm just going to check that because we already went over it. Continuous measurements, we already went over that. Two that I really want to talk about are homogeneity of variance. And all this means is, are the variances known and the same, or are they just the same in general? So for us, we have an unknown but equal case where we know the sample standard deviations, and we assume based on their ratio that the population variances are roughly equal. This allows us to use the student's t-test instead of the Welch's. If we didn't assume homogeneity of variance, or if we didn't assume variances were equal, then we'd use a Welch's t-test, which would just make it a little bit more complicated because we're not using a pooled standard deviation in our denominator. We'll get into more of that. Lastly, normality, and this is the one that sometimes gets us. Now, if you'll recall, when we have large samples, or as a ballpark, samples above 30 or something, we assume that the central limit theorem is kicking in and that normality asymptotically is going to help us, and the t-test becomes more robust to violations of normality. However, if you'll notice, we have about 10 samples per group, exactly 10, and so we can't just fully rely on the central limit theorem. Luckily, this problem gives us these plots. And these plots are basically normal probability plots. And what do they show? Well, you see on the x-axis, we have raw data observation values. And then on the y-axis, we have this sort of compressed and rescaled percentile distribution from 1 to 99. And it's basically just stretched in such a way that if we had a perfectly normal set of observations, we would expect them to fall perfectly along this blue diagonal line here. And we also have these overlaid confidence bands, which is great. And we can see in both cases that we're well within these confidence bands and that we roughly approximate normality in both scenarios. We can see here that we have some slight deviations. This is just indicating that at our tails, our values are less extreme than what we would expect if we had a perfectly normally distributed sample. But I think that we can generally be fairly confident that we have normally distributed observations, or at least that any violations or deviations from normality aren't going to really affect us that much. So I'm going to say, yeah, cool. And so now the next thing that I would do is we've verified what test we're going to use, and we verified that we're allowed to use that test without too many problems. So the next thing, if we're hypothesis testing, is to develop our hypotheses. So we have a null and an alternative. Let's go back to the problem statement. We're saying we think the new machine on average is going to pack cartons faster than the current machine. So the first thing I would do is I will just use mu1 as the new machine and mu2 is the old machine. So our null hypothesis, as is often the case, is going to be that mu1 equals mu2. And we can rephrase this as a difference, which often makes things a little bit easier to understand conceptually. So this could be mu1, and we just subtract mu2 from both sides, equals 0. And what is this actually saying? This is just saying that on average, both machines equally fast or slow, depending on how you see the world. Um, and then our alternative hypothesis, this is where that word faster is coming into mind. So actually, maybe it'll be helpful to say mu1 equals pop mean new, and mu2 equals pop mean old. Or is it current? No, it's old. Okay, cool. And so now for our alternative hypothesis, we assume that the population mean should be faster for mu1 than mu2. What does this mean? A shorter time. So it should take less time to compress 10 boxes or cartons. So we're assuming that mu1 is going to be less than mu2. Or equivalently, mu1 subtracting mu2 from both sides, this is going to be less than 0. Okay? And what does this mean? On average, the new machine is faster. Okay. And just to visualize this really quick, remember I said we're going to go slow with this. Um, actually, let me redraw that. Say this is a t-distribution. It's kind of hard to separate from a normal, but it has a bit heavier tails. Here you go. Say we perform the sampling procedure over and over again, and we get 10 observations for each one, and we construct a t-statistic each time. And say this is the null distribution of t-statistics. So what the t-statistics would be distributed as if we construct them over and over again, but where we assume that it's a zero-centered distribution. So by default, our highest density is going to be at 0. What is this? This is basically the null distribution of the test statistic. Well, what we're interested in is this region right here. This is the region where we'd have a t-critical value, where a certain percent of the observations, in this case, it's one-tailed at 5%. So maybe we can say this area is equal to 5%. 5% of the values are as or more extreme in this direction than this empirical T star. And so if our observed T star falls within this region of the distribution, then we can be fairly certain that maybe the null hypothesis isn't the operating framework for this, because it's pretty rare that we'd just get this as a randomly sampled test statistic. Does that make sense? So the point of this is just to say that we're dealing with a one-tailed and specifically dealing with the left tail when we imagine the null distribution of our test statistic. This will become more clear as we keep working with this. So if this doesn't make too much sense right now, please don't worry. Okay. So the next thing to do, we've been talking about this test statistic. What actually is it? Well, we know that our T, and I'm actually going to call this T star, and this I would call T crit. So that's our critical T value. The difference is T star, I'm just calling that to be the T statistic that we observe with our data, and T crit is like the key percentile of the T distribution that we compare it to, like our benchmark. But T star, and generally for T and Z tests, we're dealing with some form of an observed minus an expected over some degree of precision or a standard error. We can make this way more specific. So in our case, we reformulated our hypotheses right here to deal with differences. So I'm going to call differences D. So we have D, our observed difference, minus D under the null, which should be this 0 value right here. And I'm going to divide that by a standard error. Let's make it even more specific. What do we observe here? Well, we observe the difference between sample means. So y1 bar minus y2 bar. These are our estimates for the population means. And then what's our D null value? It's 0 over our standard error. And remember, standard error is just the standard deviation of a parameter, in our case, a mean. So in our case, it's going to be the standard deviation of the difference. There we go. Okay, so again, I said I'm going to be going from first principles. I am going to be doing that. So let's do some math. The first thing I want to show you is why I'm going to say that this standard error is equal to this as pooled, which is going to be equal to, one second, I'm getting a phone call. Sorry, I'm back. Okay. So this is going to be equal to, I'm not going to write S pooled just yet. I'm going to say sigma times the square root of 1 over n1 plus 1 over n2. Now, I find that in statistics classes, formulas can often feel like they come out of nowhere. So I really wanted to explain why this is our standard error. And we're eventually going to replace this with SP, which is our pooled standard deviation, which has another formula. My hope is that by the end of this, you'll understand where all these formulas come from. And even if you have to memorize them, you'll kind of understand them logically, which I think makes things so much easier. So let's do that. So remember, standard error equals the standard deviation in our case of a parameter where we've reformulated our hypotheses to be in terms of the difference of sample means. And this is equal to the square root of the variance of the difference. And just to name that explicitly, we're talking about the square root of the variance of y1 bar minus y2 bar. Okay, now let's ignore the square root just to make our lives easier for a second. We'll just bring it back at the end. Um, what do we know about y1 bar and y2 bar? We assume that these distributions of observations that make these are independent, as in we assume that the current machine or the old machine and the new machine don't have any pairings with one another, which means that for a variance calculation, we're having additivity. So for this, we can say variance of y1 bar minus y2 bar, and this goes the same for variance of y1 bar plus y2 bar, is going to be equal to the sum of their individual variances. Cool. Okay. And now it's pretty simple. Remember that the variance of a sample mean is going to be the sigma squared pertaining to it. So I'm going to say sigma squared y1 bar divided by the sample size. So this is going to be that plus sigma squared y2 bar divided by n2. Okay, so we're still not dealing with anything crazy. We're just saying that we are taking the standard error to be the standard deviation of the difference of sample means, which is basically the square root of that variance of that same calculation. And then we know that these are two independent samples, so we just split the difference and we add the two variances together. So that's where we're at right now. Now we can bring back our lovely square root. So I'm going to do that in red. And what is this going to be equal to? Well, we're going to have sigma y1 square root, oh, sorry, 1 over n1 plus, apologies, I just totally messed up my math. There's one more thing we were just talking about, which is that we assume homogeneity of variances, which means that we assume that the variances are approximately equal to one another. So this and this term are going to be equal. Okay? So what do we have? Sigma, I'm just going to say pooled, square root of 1 over n1 plus 1 over n2. Okay. And so now we basically have what our variance is going to be, or our standard deviation because we added that square root term. So basically, sorry about that last part being a little confusing. What did we do here? We basically just said this number is equal to this number by assumption. That's why we're using the student's t-test. And so we basically had sigma y1 bar squared. We can't combine them because the denominators are different. Sorry. Over n1 plus sigma y1 bar squared over n2. And all of that here. And then, sorry, equals sigma y1 bar squared. I'm still going to keep the square root over 1. I mean, times 1 over, apologies, my brain. Apologies for the quick pause. I had to go somewhere. I'm at my parents' house again. But yeah, we're back at here, which what were we doing here? We were saying that we have a standard error that we want for the denominator of our test statistic, and we are taking the standard error of our difference of sample means, which is equal to the square root of the variance of the same thing, which we can then just use the property of additivity when the samples are independent. So the sample that constructed y1 bar and the sample that constructed y2 bar, aka the new and old machines, have nothing to do with each other. So their variances in theory should add together. So here's our general rule. Oh, and this goes the same for if there was a plus here, but anyways, it would be the exact same result equals variance of y1 bar plus variance of y2 bar. So the sum of their individual variances. Okay. And so what are we dealing with here? We now have the square root of the variance of y1 bar plus variance of y2 bar. I'm just going to make that square root a little longer. Okay. And so from here, what can we do? Well, let's ignore this um, square root just to make things a little cleaner, and then we'll bring it back at the end. So if I were to erase that for a second, okay, this is going to be equal to the individual variances. And as we know, the variance of a sample mean is always going to be roughly of the form sigma squared over square root of n. And the sigma squared is for y, not y bar. So remember, when we have a variance of a mean, we are taking the variance of the observations and we are dividing it by the square root of the sample size. This should be familiar from our z-test and our t-test. But yeah, and so here, what are we going to do? Here we have sigma squared y1 bar. So this is the sigma squared corresponding to, or actually here I should probably say y1, not y1 bar, plus sigma squared y2. And each one is divided by the respective sample size. But remember here that we assumed homogeneity of variance. These should be equal. So what I'm going to do is I'm going to call it sigma squared p for pooled over n1. We can't combine it because remember our denominators are different. So we have this. Now let's bring back that square root. And this is going to be equal to sigma p times 1 over n1. This is squared, sorry, plus 1 over n2. Sorry for that random dot. And this is going to be equal to, we can bring that sigma p out of the square root times the square root of the reciprocals of the sample size. So that's just showing you if you were like, where does that come from? That's where it comes from. So this is this. And again, we don't have sigma p. We estimate that using sample. So this becomes an S of p. And we will go over how we actually get that in a second. Actually, we'll go over it right now. Okay, so that's the last thing we need. I'm just going to write this out cleanly. So what do we have all together right now? Our test statistic. Going back to here, we have that T star equals Y1 bar minus Y2 bar divided by our pooled standard deviation times the square root of 1 over n1 plus 1 over n2, right? Yeah. Okay. Now the last thing we need in order to do this is we need to know what this is. And to get that, we can follow our formula. And so fundamentally, the way I want you to think of the pooled standard deviation is as a weighted average. And so when you're constructing a weighted average, what do? You do weight 1 times quantity 1 plus weight 2 times quantity 2, and you divide by the sum of the weights, where WI equals weights. Okay. Oops, sorry. Oh, that's good enough. So that's just conceptually what I want you to think of it as. And in this case, we are weighting by degrees of freedom. And so when we have this, we're going to think of this in terms of SP squared. So this is going to be our sample variance. Now remember, for example, say we're calculating sample variance. We divide by n minus 1 because that's our degrees of freedom. Same thing when we have two independent samples. So we're going to have our weights being these degrees of freedom. So we have S1 squared, which is our sample variance for the first sample, scaled by n1 minus 1. And we're going to add S2 squared and 2 minus 1. And so if we're going back to our analogy, Q1 and Q2 are our sample variances, S1 and S2 squared. And our weights are going to be the N1 minus 1 and N2 minus 1, which are our degrees of freedom. And remember, we're just dividing by the sum of the weights. So we have N1 minus 1 plus N2 minus 1. We don't need those parentheses actually, which is going to be equal to S1 squared n sub 1 minus 1 plus S2 squared n sub 2 minus 1 divided by n1 plus n2 minus 2. We just take those two minus 1s and bring them together. So that's our SP. And so now I'm going to write putting it all together. To be very clear, you do not have to do anywhere near all of these derivations on the test. I just wanted to show you where all these numbers came from. But putting it all together, you're going to have T star equals y1 minus y2. So the difference in sample means we're going to divide that by S1 squared and minus 1 plus S2 squared n minus 1. Sorry, forgot the subscripts. There we go. Divided by n1 plus n2 minus 2. And then we are going to multiply that by 1 over n1 plus 1 over n2. Let me make sure that looks right to me. I think so. And just to bracket some things, equals pooled SD, which is SP. This is equal to D. And then I'm just going to write minus D0, but this is 0. And then this is basically just scaling our pooled SD, this right here. Does that all make sense? I can't ask, no one's here. But yeah, that is basically what it is. If you have any more questions, please feel free to talk to me about it. If you have a formula sheet, feel free to just use it. But conceptually, this is the same as our more simple t-statistics, where we are just taking an observed test statistic or an observed difference minus what we hypothesize it to be under the null, often 0, and dividing it by some degree of precision. And in this case, the main thing that changed between this and like a one sample t-test is that we have a bit more of a complicated estimate of our precision because we are doing that across two samples. So our pooled standard deviation is going to be a little bit more complicated. But yeah, now we can actually do some math. I just copied this, so we're in the same spot. I'm going to duplicate this. G has followed us, deleting that. Okay. And now we can actually get to solving this empirically. And so the way that I would start this is by working on this quality, which is SP. SP equals, in our case, we have S1 squared, which is going to be, let's see, this 0.683. And N1 minus 1 is just 10 minus 1 because we have 10 samples, so it's going to be 9. And then I believe the other one was 0.75 squared times 9. I'm just going to extend that. Divided by, this is going to be 10 plus 10 minus 2, which is going to be 18. Okay? Also, I just realized I have forgotten to put that there is square roots because remember this was the pooled sample variance, but we are taking the pooled SD because it's a standard error. So only difference is we have this over everything. Great. Sorry about that. Cool. And so when you do all this math, what you end up is 0.717. Okay? And then we can now plug that in. So we have T star equals y1 bar minus y2 bar over 0.717 times, then it was square root 1 over n1 plus 1 over n2. And here, now we can plug in y1 bar minus y2 bar, which is going to be 42.14. Let me double check this really quick. Yep, minus 43.23 over all of that. And that's going to be negative 1.09 divided by 0.717, which was our pooled sample standard deviation. And then 1 over n1 plus 1 over n2 is just going to be 1/10 plus 1/10. So that's going to be the square root of 2/10. And what is that going to be? When you do all that math, it's going to be negative 3.40 equals T star. Yay. Now that's going to land somewhere here, I feel like. Um, but the way that we do this is we're going to compare this to the critical value. So compare T star equals negative 3.40 to T crit when alpha equals 0.05, one-tailed. And if you're looking visually, one-tailed just means that you have this as opposed to this or this. And df, degrees of freedom, is going to be n1 plus n2 minus 2, which is going to be equal to 18. So that's that same number that we had right here. And if you look at the t-table to get this, let me know if you have any confusion about getting that. You're going to get negative 1.74. As you can see, we're way below, we're way to the left of this, which is exactly what we'd want if we are confirming our alternative hypothesis, or like confirming that the null is not the framework that is underlying the data. And so I will say, conclusion, at alpha equals 0.05, we reject the null hypothesis that the machines are equally fast as the probability of observing a test statistic as or more extreme than T star equals negative 3.40 should be well below 0.05, because remember that 0.05 benchmark corresponds to a critical T value of negative 1.74. So we're way below that. So we're probably actually right here. Okay. And that is everything here. Sorry for certain parts of this that were a bit shaky, but let's go over sort of the broad approach to problems like this. The first thing I'd have you do is think about whether you're using a z-test or a t-test when you have two samples and they're continuous observations. All you have to do is look for an S or a sigma. If it's a sigma, Z. If it's an S, you're dealing with a t-test. Look to see logically, are your observations paired or unpaired? And then see, are you given sample variances? And if you are, do they seem roughly equal or not? Usually in practice, again, don't quote me, but I think that you will often be using a student's t-test and not a Welch's. So often we're assuming maybe unknown but equal variances. Then what you'll do is you check the assumptions of a t-test, which the big ones you want to check are going to be normality or a large enough sample size, typically above 30, homogeneity of variance if you're using a student's, independence if you're using an independent t-test, or if it's paired, then just logically is it paired, and normality, I think we already covered. So you're going to want to check those assumptions. Then you're going to want to formulate your hypotheses. And oftentimes it can be easier to frame them in terms of a zero or a non-zero. So the way we did that was we just subtracted mu2 from both sides right here. And you're going to see if you have a one-tailed or two-tailed, and you're going to basically just try to see the shape of your test statistic. And so we know that our test statistic was based on a comparison of differences in means. From here, just assemble the broad form of your t-statistic, which remember, it's going to have an observed quantity minus what you expect under the null divided by precision or the standard error. And then you're going to fill in each of those pieces independently in way less detail than we did today. And then you're just going to calculate everything and compare it using a t-table to the threshold at your chosen degrees of freedom and alpha, and with the proper tail. And then you're going to make your conclusion. So I know that's a lot of steps, but I promise it'll go much faster if you're not writing everything out like I was. And let me know if you have any questions. And I hope that you got something out of this. If you have any criticism or think that I can make these videos better, please let me know. And I will see you in the next one. I'll hope to make one either tomorrow or the day after. All right. Bye, everyone.